Hi, everybody. Nice to meet all of you all. Thanks for coming back to the State of the Art conference. This is Bindu Reddy. I'm the CEO, co-founder of Abacus. Today, to kind of headline our conference, we have none other than Zach Lipton from CMU and James Lloyd, who is our head of machine learning at Abacus. And James is going to kick us off with a fireside chat with Zach and introduce Zach as well. So again, thanks everyone for coming, and please do post your questions or have conversations in the chat. We will pick out some certain questions and ask Zach as well. Let's get started.
Okay, thanks for the intro, Bindu. And yes, indeed, so we're joined today by Zach Lipton, who is an assistant professor at Carnegie Mellon University. Now, Zach's work covers broad plenty of areas of machine learning, so including applications to healthcare, natural language processing, but also some general topics such as robustness to distribution shift, the societal aspects, impacts of machine learning. I think more recently, causal inference and discovery, but plenty of other areas too. Now Zach, where I thought we'd start is that, so going with the working title, so neural networks, past, present, and future, let's maybe go with some present neural networks. So in particular, I was interested in your work in healthcare. So if that's a good place to start, can we talk about maybe some of the work you've done there, some of the things that you're most interested in?
Sure, yeah. Where to begin?
I mean, so you have something recent about SOAP notes, but I think so maybe the SOAP notes work caught my eye, and maybe something simple and compact to talk about.
Yeah, so it's about like maybe the methodological flavor of our lab is sort of that. I think we kind of have perhaps in a way, for better or for ill, like a pretty wide range, I think both across applications, but in methodological to like applied spectrum, which is not the same as theoretical to empirical. I think those get slurred a lot. Like to us, applications means like actual applications. Like if you're working on ImageNet, that's not doing applied work. It's doing something quantitative, but it's the interesting parts of an application have been handled for you. Just someone told you what you're trying to predict, and I told you what's available to you, and your job is just to churn on like tools.
Mm-hmm.
And I think we often like have this flavor of going into some domain and then trying to back out to what's really like deeply unsatisfying about what machine learning has to offer there, and then make that our pivot towards like a methodological spin. And so so sequence to sequence learning has become like pretty mature, and for tasks like language translation, I think we feel like we're doing better and better and have reasonable tools, but that's something that's usually performed on a kind of like sentence by sentence basis. And so the kinds of contexts that are usually fed into a neural translation system or like an order of a sentence. Then you look at like summarization and say what's going on in summarization tasks. And these are often like the benchmarks that exist are like passive convenience. So you have things like, we just crawled 10 million CNN articles, and then for each one we grabbed the lead and called that the summary, and then we took the article and called that the article, and so you look at these tasks and it's like, okay, it's summarization, but all the summaries are 1 sentence long or like maximum 2 sentences long. So this is maybe not as the kind of thing that's maybe really compelling to someone who actually wants, shares their sort of just like common idea of what actually like a summary or like a kind of comprehensive distillation of some text is. And so the context here, the motivation of the specific problem was that we have a partner, which is a Bridge, which is a healthcare startup based here out of Pittsburgh. So they founded by someone who's actually a cardiologist who then got involved in their sort of like venture and like startup incubator arm. And the kind of motivating problem is that there's been this big shift in the United States, and I think broadly towards someone asking the question, is the session started? Yeah. We're just shooting the breeze. so there's been a big shift towards electronic health records, and there's a lot of great sides of that, which is that like the records are in principle somewhat portable now. They kind of, you have maybe more confidence in the posterity than you would if they were just like sitting in a file cabinet somewhere. You don't have to find someone who knows how to use a fax machine still in order to get them transmitted somewhere else. But the downside is that of the kind of extensive digitization efforts has been that they're sort of a huge clerical burden on the doctors. So doctors, as opposed to maybe like scribbling in their pad while they're talking to someone, now they're expected to type up this kind of clean digital summaries. So they have to enter a whole bunch of structured data. They also are supposed to provide a digital SOAP note. And a SOAP note is basically it's a summary of the visit. And it kind of is a structured summary it's sort of what we call like semi-structured. It's not structured the way like structured data is, like here's a table, but it has some like informal, like or semi-formal kind of structure. Like there are certain canonical sections to a SOAP note that tend to flow in a certain kind of order, but then each one is populated mostly by like free text. So they are like the subjective, objective assessment and plan. And so the problem that we entered into and that the company's tackling is have patients visiting doctors, and the hope is that one kind of untapped potential resource is that it turns out a lot of patients actually record their visits with a doctor. So they have cell phone out and they're recording audio. And usually this is done maybe like somewhat surreptitiously with or without the doctor's permission. And they're doing it, maybe there's a few ambulance chasers out there, but I think the vast majority of people are doing it in good faith because not because they have any kind of nefarious objective, but because maybe they waited for 6 months for that visit and they're afraid of, if they might forget what happened or whatever, or maybe they have a spouse who knows more about their health situation than they do. And so they want to be, or their kids, they want to be able to bring it home and say, oh, this is the conversation I had with the doctor, and help them figure out what are they supposed to do next, et cetera. And so this offers all kinds of challenges that aren't there in the existing summarization benchmarks. So the conversations are like 30 minutes long. There are many thousands of words. The summaries are like a page long. They have this kind of section type structure. And so the question is, what can we do in that kind of setting where we have these summaries, or we're generating a page based on it's like massive transcript as opposed to generating a sentence based on an article that you could fit in a BERT model. And there become these challenges of these data sets are bigger than what even if you look at GPT-3 or anything, it's only like a couple thousand words of context that go into these models. And so then figuring out how do we work with these massive amounts of context and rip out the important parts that are going to inform some summary section. And so we ended up making use of like kind of creative use of intermediate annotations, where we have some attributions of the summary sentences to what was the corresponding like span in the input text that sort of provided the evidence of what should have gone there. And so our pipeline does something like going through the entire conversation and pulling out all the different spans that we think are likely to be noteworthy, clustering them together into groups of conversation utterances that we think together should support the same summary sentence, and then pipelining this into kind of like a translation type model. This is work with a bridge in UPMC, and that has been spearheaded by my student Kundan Krishna.
Okay, yeah, that's super cool. Basically, interesting to me. My wife is a surgeon, and so she definitely complains about some of the administrative work. And so, like, if you can reduce that burden, that would be an amazing thing for healthcare in general. But would I be correct in thinking, so in that example, like sort of very tricky to do, as you point out, like, so your input is, or transcripts of, audio recordings, very long transcripts, and aimed output is a short summary. But I guess that's one of the examples tricky task, but at least we have got inputs and outputs and an objective to maximize. But that's often not the case. So I think some of your other work in healthcare, it's not even clear, well, the inputs aren't fixed.
Right. Yeah. So, I think this is like a discrepancy between like, it's like, I think in academic work, it's very easy to sort of take the sandbox for granted, which is like we have certain canonical problem specifications and say, this is what you're given, and In the supervised learning context, usually you're given X, whatever that form factor that takes, and you're given a Y, and you want to come up with a predictive model. And if you look at that in the medical context, and I'm guilty of this too. We have papers where we maybe use the word diagnosis a little bit too liberally. And we say, like, we look at the data that's available in an electronic health record as of some point, we try to basically recognize what are the diagnoses that apply to that patient. And it turns out, it's like, if somebody's already decided what tests to run and what to write in the chart and everything else, and then, you're able to maybe do slightly better than the doctor at putting those things together to say which diagnosis applies.
So, I mean,
that was never the interesting thing, right? It's like, if you've already decided to test someone's glucose levels and test their pH, whatever, and then the machine is really mechanically able to say, like, yes, you have diabetes, or yes, you have diabetic ketoacidosis, or whatever, like, great. But that was never the challenge. The challenge was to look at a patient who came off the street, and nobody had run any tests, and decide, what tests am I going to run? And then, based on what you know about the patient and what they're telling you and what tests were already run, decide, am I ready to make a call, or do I need to run a subsequent test? And if I do run a subsequent test, what kind of, what tests should it be? What data should I collect subsequently? So these kinds of broader questions about what to observe are often, like, just not part of the ML formulation. Like, what is observed versus even missing data type work, it's usually exogenously specified. Like, this was seen, this was missing, and then you come up with, if you self-identify in machine learning training, you just throw something at it and see, did it work? And if you self-identify as like a statistician or like a causal inference specialist, maybe you start getting serious about questions of identification. You say, well, under what assumptions about confounding or unconfoundedness can I do what I want to do? But usually in a standard formulations on both sides, what's taken for granted is what is observed and what's not observed. But this is normally a choice that someone has to make. And so in a lot of work, we try to, like, endogenize these kinds of problems into what it is that we formalize. So I have some work with a student named Shantanu Gupta, and this is co-advised with an economist, and David Childers, who are both fantastic. And in this work, a main thread is, like, you have some estimate. So let's say you want to estimate, a particular causal effect or something like that. So for one reason or another, and I think there's several good ways to motivate it, like, in each round, you have to decide which set of variables you're going to observe. And so, like, you could motivate. One is like the doctor who comes in and it's like, you can only run so many tests. You can't run every single test for every person. You have to pick which subset you're going to run. Another example is you have a lot of studies where you try to estimate, have some quantity of interest, and maybe even you have in back in your head some domain knowledge. But let's say the mode of acquisition is like a survey that you're running, and you can't ask every single person every question. So you're limited to by people's attention spans. You could put K questions on the survey out of, N questions you might want to ask them. And when you start formalizing this into, like, a coherent theoretical framework, one, like, kind of strange dynamic that emerges is, what is the right data to collect? Even if you know, like, a structural causal model or something, what is the right, so what I mean is, like, you know the topology of the graph, but you don't know any of the actual parameters. What is the right data that you should collect to get you efficiently to a good estimator? Depends on the unknown parameters of the model. And so there becomes, like, an interesting loop of, I got to collect some data, learn something about the world so that I can make better decisions about which data to collect, which in turn bring me closer to knowing which data I should have been collecting in the first place. Mm-hmm. And so, like, these kinds of, loops. Another paper we have is with a operations research student named Kira Gan, and some other folks in the operations research group at Tupper at CMU, and there the motivation was something like, often, like, a postulated confounder is something that, like, could be retroactively observed. So something like, like, is there a gene that causes you to smoke and also causes cancer? And it's not that smoking causes cancer, it's the smoking gene. Well, running a genetic test maybe is expensive, so you can't do it for everyone. So we have a setting where, like, imagine you have passive data where you see the treatment and you see the outcome, but there's a postulated confounder. And now you want to go in retrospect and basically you want to, as efficiently as possible, estimate the treatment effect of the treatment on the outcome. So one thing you could do is you could just throw out all of your old data and go collect some new data. It's more expensive where you run the test for everyone. But another thing you could do is you could be active in your selection. You could go back and look at your test and say, oh, I'm going to start calling up certain patients. And based on the values of the treatment confounder and like the observed covariates, make strategic decisions about for whom I want to run this genetic test retrospectively. Then you say, is there an advantage to incorporating this partially observed observational data and, you know, an active selection process versus just like saying, oh, it's confounded, it's hopeless, throw it all out and collect a new data set where everything's identified. It turns out there are statistical benefits to like incorporating the observational data you had on top of, you know, the small data set for which you've strategically chosen for which examples to reveal the values of the variables. So, you know, high level is that like I think these decisions they're pervasive. Like you decide whenever you interview someone for a job, you say, am I ready to make a call or do I need to do another interview, or do I have some unknown? Like this is a fundamental aspect of human decision making that we just sort of throw out the door. We just don't even think about it, you know, because problem formulations could give us blinders, right? And so I think this is something that you know, we try to work a lot on figuring out, like, how do we sort of, you know, not just like come up with more efficient solutions or tighter bounds or better quantitative results, but how do we like grow the borders of the problem formulation to encapsulate some things that we find unsatisfying.
Yeah, that's very interesting work. Just to dangerously anthropomorphize potentially, I'm intrigued, like in that work where it's sort of subsequently choosing what data to acquire and observe, and as you point out, some of that early data might be to reduce uncertainty in understanding which data to then collect. Do you observe sort of exploratory behavior initially early on? Have you observed cases where maybe it looked like it was going with one hypothesis, but then it got a contradiction and then it had to open things up again? Do you use behaviors, or do we learn like different ways of decision making? Like, does it look human or does it not? I guess is my question.
It's sort of like we do have those behaviors. I would say we learn them so much they're like a fundamental aspect of the algorithm. Like not absent those behaviors, you might not be able to make the kind of guarantees that you'd want about like the regret that you would have, right? Yep. So it's not so much that it's not like we have a meta, you know, algorithm that's deciding what is this, but rather that the proposed algorithms that we're able to analyze and show that they actually converge to zero asymptotic regret are premised on the very they're based on the very premise that like, you know, so for example, one of the simplest things you could do is like an explore then commit type approach. So this is like one of the simplest things you do. You say, okay, I've got a horizon, any horizon, whatever it is, but of length t. So for something like root t instances, I'm going to sample them, you know, something like uniformly at random among all the different data sources. Then I will have some beliefs about the parameters of the model, and then thereafter I will exhaust for the very rest of the horizon. I will choose what, you know, basically to sample according to like whatever is the optimal ratio among the different data sources.
Okay. Based
on those current beliefs, and obviously like as the total horizon would grow, that root t fraction would also be growing, and you know, so it's like the longer the horizon, the closer you are to doing perfectly. But in that case, it's like, you know, then there's more subtle things that you could do that actually in finite samples make a big difference. Like instead of exploring and commit, you could do like a sort of explore then greedy, where you have an initial exploration window, but then thereafter you continually update your parameters. And so we have kind of analysis of these different algorithms, but it's sort of fundamental that like you need to have this exploration period, because if like imagine you just do greedy from the start, like you just say like based on my current beliefs about the parameters, I'm always going to collect according to the data source that I think is going to sort of like most rapidly drop the variance of my estimator. You could wind up in a situation where you have some initially very misleading beliefs, like you just got wrong. You thought that I don't know if I'm going into too much detail or not, but like you can have situations where like you have two data sources where basically if you only select from one or you only select for the other, you can't even estimate the thing you care about. Like the causal effect you care about, the estimate, or whatever it is,
Mm-hmm.
really depends upon observing both data sources. And the question is like, how do you allocate your budget among them to get the most accurate estimator? This is like classic kind of data fusion problems that like show up in economics. Like I have one data set where I observe the instrument and the treatment, and then another where I observe the treatment and the outcome, and I'm able to stitch them together somehow.
Yeah,
you have other situations where it's like the solution's on the corner. It's like either the optimal answer, either you should only choose one or you should only choose the other. And the danger is like if you end up misestimating the parameters such that you think that you should always pull this guy, and you really need to pull this guy a few times to realize that like you were actually wrong and you should have been collecting some data from there. It's like, well, like if you're purely greedy, you'll never collect the data that will reveal to you that you were wrong in the first place and should have been collecting something different. So it's like you can't have this sort of thing if you don't have a built-in exploration period where you have errors that you can't recover from. So it's not necessarily that the model is learning the exploration strategy so much as we're posing one and showing that this leads to an optimal estimator.
Got it. Okay, so more of a algorithmic design, proving things about that design, and like naturally it's going to have some exploration, otherwise you won't be able to prove any of your regret grounds. Okay.
Right,
cool.
right.
Yes. Okay, I was maybe imagining the emergent, reinforcement learning style version of things, but potentially we don't have quite access to that data because we can't just simulate these things.
No, I mean most of I think the classic RL algorithms actually it's not all that emergent, right? Like they like epsilon greedy or even policy gradient, they would have something like some entropy regularization to encourage regularization that's attenuated over the course of learning. So it's often I think it's hard to find a RL algorithm where people haven't somehow or another baked in their
that's a fair point.
Exploration strategy to some point.
Potentially a pretty meta RL algorithm before that started to move.
Right.
Okay, and also yes, one of the details of that work. So if you're sort of choosing what data to observe at any point in time, do you have any sort of are there any sort of tricky points with how to represent the data that you're working with? Because one test comes back with data in one shape, another test comes with it in a different shape. Is that a consideration or not really?
Yeah, I mean, like I want to how put it. Like I think the like short answer is sort of like in our like initial studies to even formalize this problem, we kind of address a fairly simple setting there where it's like, okay, let's pose a graphical model. Let's even like start off looking at like say like linear Gaussian models or something like that, right? And really understand these things. But again, right, like there's sort of an assumption that you even already have the right higher level representation of your data such that it's even, you have the right features of interest such that they fit into the sort of structural diagram you could draw like over, the sorts of things, the right entities about which you have domain knowledge. And I think that like this is just generally like and so I don't want to overstate like what's accomplished in our work. What's accomplished in our work is kind of like setting up that problem and giving it a kind of proper theoretical treatment. But there's like, I think what you're pointing to is this like, there's this leap between, I think, like causal inference and this kind of structural type learning where we actually can say things that are like coherent and like a little bit philosophically more satisfying about, whether it's strategic behavior, whether it's estimating causal, there's all kinds of things we could do that actually make sense, but they all make sense if you live in the world where data is kind of simple and you have the right representations about which you can express prior knowledge and stuff like this, or even structural prior knowledge. And then we have like the kind of deep learning world where people are kind of, when it gets to these sort of more, systems-y type problems doing absolute nonsense, but on the other hand, what they're contributing that's really satisfying is that you could touch real data. And so I think that there's this binding between how do you achieve any of what's exciting that sort of literature and like causal inference and more like stylized models give us the ability to think about coherently, and at the same time bring it to bear on the sorts of data that doesn't come neatly packaged into the right sort of variables, that they're the variables about which you would draw such a spell out a structural model. And some of our work kind of tries to bridge that gap a little bit, like use some of the intellectual moves, if not the actual mathematical machinery of, say, like the sort of causal inference in a setting where we really have raw data and deep learning models. And I think like our work on counterfactually augmented data is a little bit of that flavor, where we're saying, how do we use the intellectual tools of causal inference to think coherently about a problem where, a community seems to be spinning its wheels, but at the same time, we want to work with real data, and we want to work with real models, and we want to be able to say something that has an impact on that side of the fence.
Yeah, good that you mentioned the counterfactual stuff, because that was just coming to my mind as well when you're sort of talking about, like, it's all related, semi-related to, what data do you observe? But yeah, could you speak a little bit more about the counterfactual work? So it's super cool, I think.
Yeah. So I think there's this problem that we train predictive models. Like, this is the one hammer we have. Like, if someone's, I think almost anybody who's got a ML job at industry or did a boot camp or did a master's degree or anything, almost probably the 99% of like day in, day out is like training supervised learning models, where basically you're just saying, looking for like minimize loss, on some data set, do a post hoc evaluation, see if you generalize. That's like kind of the only move. And it's like the thing we're good at is like, minimizing error and checking to see that we actually did minimize error. And that's like this, we had the machinery for it. We had the machinery for it under, even then, only under kind of really restrictive assumptions like IID. But we have some tools that work. And I think what's the problem is that this isn't the only thing we actually care about in the real world. So we're going out, we're taking this hammer, and we're building all these models that are then being used these models, first of all, almost none of them are actually in a straightforward way addressing any kind of decision problem. So we're almost always committing some kind of like intellectual crime of telling people we know how to automate a process, where what we really know how to do is make a prediction under the assumption that nothing ever changes in the world, and the historical data that we have is totally representative, and that it's almost like our normal like way of doing things in ML is predicated on the idea that no one will ever apply the model for anything, because God forbid they should apply the model in any way that fed back into the environment, then the model would invalidate itself by virtue of having been applied. So I think what you're getting at is like, we have people, we're really interested in making all kinds of decisions, but we don't have decision model or predictive model. We have all kinds of desiderata that are about, the bases on which decisions should be made, are decisions justified, or are they not? That's not what's happening in supervised learning. That's not what's formulated coherently there. And so people are kind of coming up against these concerns, whether it's like the model is susceptible to spurious correlations, or the bad correlations, or the model's bias, or the model's, but the problem that you have is, it's not that people are wrong that in saying that these are problems. Like, there are real problems. The problem is that people don't have the right formalism for, like, they have no idea what they mean. They're using the word bias, but it's not statistical bias. Then, like, what is the right way to operationalize technically what we mean? Like the sort of thing that they're calling, or what is the bad correlation?
Mm-hmm.
People say that the model depends on the spurious signal, but they don't mean spuriousness in the statistical sense. In stats, you'd say a spurious finding in a pure statistical, I think the most common expression would be like, this is something that was like an artifact of having a small sample size disappeared when you had more samples.
Mm-hmm.
But that's usually not what people are talking about when they say the model depended on texture and not on something else. This isn't something that goes away when you have more data. It's something that like it's like, this is the model that you're getting. Conceivably, it might even be the model you would get if you optimize the neural network for that task with 1 trillion examples on that distribution, or 10 trillion examples. So we try to, we took some inspiration from the literature in causality, where like spuriousness actually has a more coherent meaning there, right? Which is something that's sort of a spurious association owes to confounding.
Mm-hmm.
So rather than to a direct causal relationship in either direction. So you could imagine like, am I going to repay a loan? And there's, let's say some features are, what shoes am I wearing? And another feature is like, what is my income? And the outcome is, do I repay the loan? And so the question is like, well, what does it mean for like the shoes to be a spurious signal? Like, well, you say, oh, it's not right. You shouldn't be making the decision based on what shoes people wear. What if, and so like, well, what's so unsatisfying? What's wrong with it? One reason why, in a statistical sense, like it's not spurious. It's like, this doesn't go away. Shoes are, at least in my fictional universe, like if you wear Oxfords, you're more likely to pay your loans than if you wear sneakers. Except for if you live in Silicon Valley, and if you wear sneakers, you're more likely to pay your loans than if you wear Oxfords. But
yeah, I think in this particular example, the correlations might be really quite nuanced here. But
yeah. But the point is that, like, there could be a real association. It's not spurious in the sense like it doesn't go away if you have lots of examples. The sense in which it's bad is like a causal sense. Like, this is not what actually causes you to repay your loan. If you took someone who would otherwise wear Oxfords and you put them in sneakers, they don't become less financially responsible, or you don't lower their earning power, and you don't lower that, so maybe there's a confounder, which is like, what is the person's occupation, which influences their income and in turn influences whether they repay. It influences their shoes, but that doesn't influence what they repay. And so part of what we're getting out, in this question is, we might even ask ourselves in the first place, when is it even identifiable? Like if I just drew this out as a causal diagram and I have A and B, and A and B are my observed features, and A causes the label and B does not, can I actually determine this just by looking at the joint distribution of A, B, and my label Y? And it's like maybe or maybe not. Like if the features are noisily observed, the answer is no. I cannot determine does B have a causal relationship with Y or not just by looking at the data. Then the question is, what could we do? And one thing that you could do is you could say, let me live in the simple worlds that have like 3 or 4 or 5 variables, and that's what my data looks like, and I know the causal diagram. What we do with the counterfactual augmented data is something different, which is we say, well, with natural language, the data doesn't come packaged in that world for us. It doesn't say, here's the sentiment and here's whatever, and you could directly turn these knobs. But humans actually sort of do speak about text in this way to each other, and humans are the generative model for text. So like if you wrote a recommendation letter and I said, oh, this is a little bit too gushy, tone it down, you could go and you could tone down the gushiness, like leaving other kind of aspects of the review, all points of fact, all accounts of the projects or whatever, unchanged, you say, or the other direction, make it more enthusiastic. So the point is that we kind of speak about text like it has these disentangled factors and we know what they are. And so then the question is, can we leverage humans in the loop in a more maybe elevated way? So part of the thrust of the study is to say, instead of going on MTurk or wherever and saying, I want you to just annotate stuff, like, is this a positive review or is this a negative review? What we do is we go into this cross-parsing setting, we say, here's a review and its original label is positive. Here's the same review pre-populated into an editable text box. And here's a target counterfactual label, which is negative. And my goal is I want you to edit the review in such a way that basically you don't change any aspects of the review unnecessarily, that aren't, you didn't need to intervene on that aspect in order to change the applicability of the label. But, nevertheless, change the label so that it's the resulting review, edit the review so that the counterfactual label applies and not the original label. And then, and so here's an interesting thing that happens. If you train it's just a normal associative predictive model on Rotten Tomatoes reviews, you find that let's just say you do a TF-IDF model and you look at the coefficients. So horror is super predictive of a negative review and romance of a positive review. These are just genres. It's like you could have a really, there's no shortage of bad, romantic comedies or whatever, and there's no shortage of great horror films, namely the entire Jordan Peele canon. But the point here is that this is like a spurious association, and probably a lot of things, like maybe horror films tend to be lower budget, and so on and so forth. But just being a horror film doesn't mean that it's a negative review. But it is associated in the data, and a predictive model will pick up on it. So if you then you take all the reviews, if you now look at for every original review, we have its counterfactually revised counterpart. And there, every negative review is now a positive review. But all those negative horror movies that are now positive reviews, they still say that they're horror films. And this is because the human kind of knows what we mean in terms of the disentangling, like the things that matter and the things that don't. They understand that genre is not something that needs to be intervened upon in order to flip the, the sentiment label. And so they don't intervene. They don't change. They don't edit the reviews in such a way that change the representation of the genre. And so if you train a model in the resulting data, you actually find that horror is a super positive feature and romance is a super negative feature. But other words that are generally super positive and super negative stay the same. So you have like fantastic, excellent, whatever, but now horror is up in the top and you have terrible, awful, whatever, are still at the bottom because those things were edited when they changed the review, whereas the genres were not. And the interesting thing is if you train a model in the original data, it performs well in the original data and goes down to like the level of random guessing on the revised data, and vice versa. You train a model in the revised data, it does well in the revised data, goes down. However, you can actually, if you train on the data combined, find models that perform almost at the level of the best model on both the original and the revised. So this is what we call like the counterfactually augmented data when we pool it all together. And so essentially what we've done is we've sort of like de-separated some of these other factors from sentiment, in a very kind of gestural way. Like we didn't do the do calculus, we did a crowdsourcing experiment, but like in a kind of, at least at a high level, like kind of stylized way of thinking about it, we've sort of decorrelated all of these otherwise associated things by virtue of doing this intervention.
Yeah, that's very interesting. I mean, it reminds me of statistical process of matching, of like, gathering a data source, but making sure that every data point is matched against another data point, which, maybe only one thing changes between them.
Right. It's all kind of like very different approaches, but of like trying to get back through various strategies towards the sort of thing that maybe like an RCT would give you for free or something.
Yeah, exactly. So in a statistical case, like, you're trying to avoid like, learning non-causal things, but in this case, it's sort of, this can be a solution to picking up on bad bias. So when people say bias is a bad word, this is a potential alleviation to it, which is cool. Alrighty, looking at the time, I should see if we have some questions, which we do. So we have some in the Q&A, which I'll take a look at now, and then I'll trawl the chat. Okay, so I'll have a read through them. But the first one, I'll see what you make of this one. Is there a way to make learned models as data independent as possible? I'll have a read further down.
Yeah, I'm kind of curious what the questioner means. I'm sure there's some reasonable interpretation, but it's like the on its face interpretation of in a sense the whole purpose of doing machine, like the learned model is certainly dependent on the data, in that if it weren't, it wouldn't be machine learning. So I'm not 100% sure. I mean, there's some things I can imagine you might hope for, like, for example, you might hope to come up with algorithms that require as few, for example, say hyperparameter choices or anything like that be custom specified on each individual data source that you might attack. But of course, the learned model itself is a function of the data, right? Like you can think of machine learning as like a meta, it's like if a model is a function that maps from a data point to a predicted label, the machine learning algorithm is a function that maps from a data set to a model. And so the model is, there's a direct line, you feed it in a different data set, you'll get a different model. And that's the whole point in the first place, right?
Yeah, I'd agree. I think, the simplest formulation, if check out Bayes' rule, the data's there. So I think it has to be part of this. Okay. Good question here. So are there well-known techniques for translation, dealing with non-standard contextual scenarios, so custom acronyms and labels? Is that something you've had experience with? So I know you've done some NLP work, but yeah, how does modern NLP deal with very niche contexts, I guess? That might be true in the medical domain, of course.
I mean, I think there's a lot of things that maybe sort of touch on this in different ways. I mean, I think one thing is that a a lot of models, especially in like translation context, are equipped with things like copy mechanisms that allow them to sort of predict each next word out of like the vocabulary, but also have an additional sort of like the softmax like sort of represented as a mixture of a softmax over the vocabulary and a softmax over the input context. And so this allows the model to just like a kind of facile route to be able to directly copy paste, word pieces or words out of the context into the target. And copy mechanisms are, whoa, Charles Elkin just popped onto the screen. My advisor. I think I'm in trouble. So these hey Charles, so the copy mechanisms are quite popular, especially in summarization. I think that's partly because in summarization type models, you very often can get quite far just by generating a few kind of glue words and lifting the right phrases out of the source documents.
Okay, and we've got one question here. Is it clarifying question?
I'm sorry, just as like a very minor point that in general, the movement in NLP away from words as tokens towards word pieces of tokens has slightly lessened some of the magnitude of some of the worries about like out of vocabulary, because the word piece vocabulary is expressive enough to construct any token. So now obviously if you're like in the future and you're encountering like a word you haven't seen before, like ever seen before or something, it might still be hard to get a model to predict it, but it's capable, at least in its output space, of expressing it, which solves some, if not all, cases.
Okay, so we have a clarifying question here, which I think, so the question was just, in which phase of machine learning would the counterfactuals approach work? So the question was post-deployment, but I think that the main point, as you were saying, it's a data augmentation strategy. So right at the beginning of the data, like, unless I got it wrong.
Yeah.
Yeah.
And there's value to doing research that gives you like a ready-made tool. It's like, okay, go deploy this right now. And I think in some ways there have been times in our research community where we were paid a price for being too far removed, having too little footprint that was close to things people could actually use. And I think, though, this is one of these things that requires some moderation, and that it's very easy to like embrace a sort of equally silly orthodoxy that like all research should be like on the precipice of product deployment, and that's the right place for research to sit. And I having like fingers in a few different pots that are at different points along the spectrum, from like kind of basic conceptualization of certain things to kind of very practically deployable things. Like, for example, our summarization models from, I think, the SOAP notes are actually quite ready for deployment in certain contexts, or at least would be an improvement over the state of the art in certain kind of contexts. With the counterfactual augmented data stuff, I mean, I think there are ways to apply it, but I also think in the first place it's like a powerful sort of just clarifier of what the hell did we even mean in the first place when we say the model's depending upon the wrong patterns, the bad patterns. A lot of this stuff, it's like you see the sort of like confused language that emerges, I think, whenever like a formalism comes up against concepts that like you have the wrong language in the first place. You're not even capable of talking about the problem that you care about. I think Yuta Pearl talks about this. He's not very charitable to statisticians, but he talks about this a lot. And I think he's right about this to some extent, that like you look back at a lot of texts, people trying to talk about causality without actually having a primitive in their formal language that represents an intervention. And all that can happen is people spin the words. There's a lot of value to just even clarifying like what the hell are we even talking about in the first place. And I think that's kind of maybe where we've gotten so far with the counterfactual augmented data stuff, of putting some really powerful like illustrations of like like a useful way of conceptualizing what the problem is. Now I think actually going from that to like a ready-made solution for like where does this fit in the ML lifecycle pipeline, whatever, I think requires some thought I'm reluctant to give like sweeping advice without like focusing on a specific problem and thinking what is the relevant counterfactual and how is this model being used and what is a reasonable basis for me. There are some contexts where just making a prediction based on whatever is most likely under an IID assumption using all available data is the right thing to do. There are some contexts where that would be a violation of like concepts of procedural justice and things like that. And, I think without knowing whether you're just trying to forecast horse races or decide who should go to prison or grant loans, it's hard to say whether you even should be using counterfactually augmented data at all.
Cool. Well, thank you for that. So I think we've now got both speakers for the next session. So with that, I'd just like to thank you, Zach. That was really fascinating discussion of some of your work. Thanks for sharing those thoughts.
Yeah, thanks for having me.
Alrighty.
Thank you, Zach. Thank you so much for coming. Hopefully you'll come back to one of our other conferences later in the, later this year or early.